Okay, good morning, everyone. How are you? Okay, not LPR positive. Okay, but before yesterday, when you try to, yeah, there was a time. Great. What happened? Back in the kind of mine, the engineering school has some kind of accreditation program. So they had a lot of people coming on Malta, coming in Malta, and alumni as well. That's why we had an explosion in cars. They were accused of BRT, they were accused in during the one. So very miserable. And that ended yesterday. Basically, we'll see. Hopefully, it doesn't last for the rest of the semester. Okay. Okay. We'll start with part A first. Then we take a break after this so that I can check your work. All right. Okay. The first one, OLS, ordinary least squares method, estimates the linear equation parameters by minimizing the sum of squared residuals. That's the formula. You should be familiar with it. SSR, sum square residual, will minimize that. U square and so on and so on. Where U is by definition is yi, the observed y, minus the model y hat, right? Either you see it as y hat or you see it as beta, the combination of beta and the x, which is the model. Y hat is equal to beta naught hat plus beta 1 hat xi, x1 plus beta 2 hat x1, and so on and so on. And that's this part here. Okay, good. Right. Usually you will see u is equal to 1 minus u hat. But this is u hat. Right? The model is u hat. The betas and the x's is u hat. And this is written in a simplified vector matrix form, where the beta here, the vector beta, really written in full and it's vector, are all the collections of the betas, non beta 1 and so on. And the x are all the x's, right? And the dimension is k plus 1 times 1, k plus 1 by 1. Why is it k plus 1? What is k? What is the plus 1? Number of variables. Which one is number of variables? K is number of variables, that's right. The number of x variables. Okay? The same as when you have degrees of freedom, n minus k minus 1. K is number of variables you have in your regression. How about the 1 part? That's the constant. Right? All right. Now, the question is, why can't we just skip the squaring and just get the sum of all the residuals? We want to minimize residuals, basically. Minimize the error. Makes sense. Minimize the error, you get a better model. Why don't we just sum them up? Because they will cancel out each other. Because the residuals are the distance between the actual values and the best fit line, the regression, straight line in the middle. So, since the lines in the middle, there will be some positive residuals at the top and negative ones at the bottom. Whichever one you calculate. And overall, they will cancel out. You end up with the sum of 0. If you square them, what happens? Why does squaring solve this problem? Because all square values are positive. Right? That's what you do. All right. Any questions? Okay. Okay. We have this file here, teacher ratings. Basically, you're asked to not consider credit and whether the professor is good in English and whatnot, and just look at how good looking the lecturer is. So investigate how model evaluations, basically your SETU, are related to your professor's duty. So if Shanta is pretty, you like you give her a high SETU score. Something like that. All right? Okay. Now. All right. So this is a scatter plot, the exploratory. Can you tell what slope it is? You can tell now because there's a regression line there, right? But without that, you can't really tell that. Yeah. So there's a slight positive relationship. Okay. So if you can't really tell this by the naked eye like that, the regression line, it shows that there's probably not a lot of relationship there. Yeah. Which makes sense in this context. So let's run a regression, cost valuation on beauty, nothing else. Okay, so what do you see here? R square is quite low, 3.6%. It's not a very good model, but it just, yes. Huh? Oh yeah, that's good. Stick there. Oh, you're right. So beauty should be on the x-axis. Thank you. Okay. You guys okay with this? You guys got this right? I got it wrong. Okay. I mistakenly put the axis wrong. Okay. That's correct. Thank you. Do I have it here? Okay. I don't have it here. Anyway. Thanks so much for pointing that out. So please do the correct one. Okay? So the y-axis should have the y variable. Okay? The y, the variable that is being affected, being predicted, being estimated. The cost value should be here, and beauty should be here. All right? Okay. Sorry about that. Does the shape change much? Not much, right? The relationship is still positive, and it still looks quite random. Okay. All right. Thank you. All right. So now, R square is low, but interestingly, is statistically significant. The p-value is 0, right? So intuitively, we wouldn't think that the lecturer's appearance would be a factor in your cost valuation, right? So why is this significant? For some people, maybe some people want to do a small fraction. They might consider that important, right? And that's why people like to go overseas and go to France, all the lectures there. And looking at the Hazim, it's back. They like it, so they go there. Maybe, but we would like to believe that that's not a general thing that people look for. You like the quality of the units and how well they teach, right? Okay. But here, is significant, shows that it is something that most people actually find important. It's not a fluke. It's not just a few people. It's everybody. It's something that everyone considers important. How do we explain that? What do you think? First, you can consider, is it a good model in the first place? Is it a good model? Definitely. No, why? The R square is very low, right? 3.6%. That's very low. There's hardly any. It's very low R square. So what does that imply, low R square? So simple regression, just one variable. Do you think this is the only factor that, right? It's not even one factor. There are a lot of other factors. Actually, those factors are listed in the question here. So it's not a very good model. There are a lot of important factors being omitted here. Okay. Then what? Where am I getting? The Vegas level? Yes. It is. So it is significant, right? But intuitively, we wouldn't think that it would be significant. You know? Some people might find appearance important, but not everybody. It being significant means that everybody thinks. Yeah. So we get to why are we getting this significant results here? Something that we have kind of explored. It's not a very good model. So there are other factors that we're not taking into account. Right? Any error? 0.025. This one? Okay, yeah, that's why we get a we get a IP standard for Ruby, right? That's all true. Why do we get it? Okay. How omitted variable bias? Yes, is it possible? Because there are a lot of other factors that are not taken into account here, and we not include this variable beauty might be capturing the effect of other variables which are relevant, teaching quality, course quality, feedback, things like that. Things that you actually find important for course. So since we have excluded all that, we put only one, so this might be capturing the effects of others. That's why it makes it negative. Sorry, significant. Right? So the context is important. Since you understand that it's doubtful that beauty is such an important factor. You have to investigate. So you can just take this result as it is. Right? If you add all the other important variables, it's very likely that this will not be significant. Right. Understand? Okay. And R square will be higher as well. It's very low R square. Okay. Okay. If when you add the other relevant factors and beauty is still significant, then that's interesting. Oh, it is still significant. So please, students do find that important. So university should hire good looking lecturers. So I'll be fine. Okay. So that would be something interesting, right? So then you can conclude, this is interesting finding. It's counterintuitive. But if you just put one and it's significant, you get excited, then that excitement is not found. You could be wrong. Okay. All right. Okay. So here, related to what we have done last week, shows here that why is it that the coefficient here is the same as the mean of y. Last week we saw that if you regress y on only intercept, then you get this, right? But now we have an x variable. Why does this happen? That's the question here. Now, this is actually a coincidence. First of all, beta naught is calculated in that way. Okay, let's just rearranging this equation here. So you take this and put it over there. So you have beta naught is equal to y minus beta 1 x1, right? And then beta naught is calculated by taking the mean values of all the variables, y hat and x, y bar and x bar. Okay, so that's how beta naught is calculated. And it just so happens that for this particular question, the mean of beauty is 0. 6.26. That's a very small number. You have a number, right? It's a big cutoff. But basically, that's 0. Very close to 0. So since that is 0, so times beta 1 hat, that whole thing is 0, and therefore beta naught has equal to the mean of positive evolution. Right? Yeah. So just for this particular regression, that this happens to be 0. But for other regressions, no, this is not always the case. This is always the formula. This formula is correct, but this value will change depending on what the mean of that is. For example, we look at some random regression. This, for example, so the intercept here is negative 43, and the mean dependent variable, the mean of one variable here is 13.5. So they're not the same mean, right? Because the value of this, mean of this are not 0. Okay? Just for that particular question. All right. Okay. All right. Does beauty explain a large fraction of the variance in evaluation across modules? Well, what do we look at here? R square, right? Obviously. So 3.6, not very large. So no, not large fraction. Okay, question 3. Um, this is looking at the effect of small class on test scores. So the idea is in education, one of the biggest ideas is that we need smaller classes so that the teacher can give attention to the student, right? Like good universities will have this kind of benchmark. So like Monash, we have from 25 to 30. That's the maximum. So this your class here is about 30. That's the maximum that we can go, which makes it more expensive, right? We need more labs, we need more teachers to teach, more hours, more labor costs, which is why good universities are more expensive in that sense. But that's one of the reasons, right? When you go to school in primary school, my class has like 40 students, right? Because the government don't have a lot of money to pay students. When you go to national school, you have smaller classes, right? If you go to Oxford, for example, you have one-on-one with a tutor. Yeah, it's not even a teaching session. You learn yourself. You come to class. You have some issue, some topic. You discuss with the lecturer or the tutor. It's more like a like a debate, like just talking and discussing ideas. It's not a teaching session. So if you've gone to any interviews for Oxford or Cambridge, they sit you down. They give you some questions. Sit you down and one-on-one with the tutor lecturer. See if you can talk to them and discuss how to solve that problem. They won't teach you. They just guide you a little bit. Let's see if you can get them. So that's one of the interviews. Yeah. So the idea is smaller classes, better performance. All right. So that's what we're looking at here. All right. So small class is a dummy variable. So a small class is defined as having approximately 15 students, and regular classes about 24 students. All right. So do small classes improve test scores? Ah, is it positive? The beta? Yes, it's positive, 13.9. Right. So if you have a small class, on average you have 13.9 points higher test scores than a regular class. And to put it in context of how large it is, see here, is approximately equal to 1/5 of the standard deviation in test scores. So it's a moderate increase. Okay. So this is one way of putting it in context. You can also put it in context of the mean of test scores, for example, right? Like what we did with the soda price a few weeks ago. So here the mean of the score is 925. So 13.9 out of 925, is that large enough? Is it small or is it big? It's not very big actually. It's quite small, right? Yeah. Right? 1.5%. So you calculate, that's good. So 1.5%. That's not very big. Okay. Another way of doing it is comparing to the standard deviation, because we consider standard deviation as the natural fluctuation. So this means that you will fluctuate by this much anyway. So anything less than that is not very significant. You know what I mean? Right? Because if you change from class to class, you will get variation of this much anyway. That's standard deviation, right? So if you want a real effect, it should be an increase of larger than this. You get the idea? So here we 13.9 compared to 75 is about 1/5. And here it says a moderate increase. But I kind of disagree. So this is not a really significant increase, right? It's smaller than standard deviation. You get that much variation anyway. So it doesn't do much. All right. Let's do an hypothesis test. Is it okay? Too fast? You want to follow? Okay. 5% significance level. So we're testing now hypothesis of H naught of beta 1 equals to 0. So beta 1 here, 13.9, where the test is that significantly different from 0. Okay. We compute a t-stat, 13.9 over 2.5. All those two numbers are given here, 13.9, and that's 2.5, and the error. Okay. Usually, the one put here is the standard error, but sometimes they put t-statistics straight away. So you don't have to record the t-statistics. So be careful. Read the question carefully. Okay, they might want to catch you and trick you with that. Just be careful. So 5.56 and we use the critical value approach. We compare this value with the values from the distribution with the degrees of freedom n minus k minus 1. We have 340 and 840 minus 1 minus 1. So 3, right? Degrees of freedom. Do you know how to look up the table? Any problems? Yeah. I assume you're okay with it. Okay. If you're not, just let me know. You can find me later, look for your past leaders. But no problem. The degrees of freedom. And since it's quite large, it's 40, it's very close to the normal distribution value of 5%, 1.96. You won't find 838 on table, right? Yeah. The maximum is probably 120 in the t-distribution table. Degrees of freedom. Because anything beyond that is quite close to the normal value already. The one at the bottom, yeah, this says normal or it says infinity. So that's the value if it is a normal distribution, 1.96. So 5.56 is larger than 1.96. Therefore, you reject the null hypothesis and conclude that small class has a significant effect on test scores. Okay. Now, what's the difference between this analysis here, this test, and this analysis here? Right? So we say there is a statistically significant effect, but here we also say that the effect is not very large. So this is a little bit of statistical significance versus practical significance or economic significance. Economic. What's the difference? Can we say that this is a small effect and this is significant? Which is what kind of what's happening here. Yes, we can. Right? Statistical significance meaning that it happens every time. It's a real relationship. Every time you have a small class, it does increase by 14 points there. It always happens. But that 14 points is a small gain. It's not impactful. You get what I mean? Right? Can you have an impactful effect but not statistically significant? Yes, you can. It doesn't happen all the time, but when it does happen, it has a very large effect. Right? Just like if you're taking medicine, we lose medicine. You lose weight, but you lose like 100 grams. One impact. Another one, if you take it, only 1 in 100 people will get the effect, but you will lose 10 kg at 1%. But the rest will not lose anything. You see what it is? See the difference? So that's the difference. Something like that. So those two things are not the same. You can have both without the other. With, theoretically speaking, academics usually, they want to look at statistical significance because we're trying to establish the causal relationship. If there's no statistical significance, it doesn't happen all the time. I mean, there's no causality. It just happens by chance. Like just 1 in 100 person get the weight loss. Just that 1 person. So it's kind of by chance. Maybe that person has some special body biology that's compatible with that particular medicine. But it doesn't happen for everyone, for example. But in practice, some people they want the practical significance, the impact, right? But it's dangerous because it doesn't always happen. It's like a gamble. You either get a very large effect or you don't. Nothing. So ideally, you should get both, of course. That's two things that you can think about when you run model system. All right. Any question? Okay. Okay. Construct a 99% interval. So that is the formula. which is the same as the formula you've seen with x bar, the mean, right? X bar plus minus critical value times the deviation. So it's the same here. Like here, you have beta instead of x bar plus minus that's the critical value e and the standard error of the beta. Okay. So beta hat is 13.9 plus minus 2.58. 2.58 is the critical value for 99%. So alpha is 1%. Okay. So from the table, we can look for 1%. 5% will be 1.96. Right? So this is 1% times 2.5. That error. So we have the range of 7.5 and 20.35. So how do we interpret this? We see that we are 99% confident that the true value of the effect of small class on test scores lies between 2.75 and 20.35. Okay. Before this, when you interpret the mean, you say the true mean of the population, right? Remember? First year. So it's the same idea here. Just change the true mean of the population to the true effect of small class on test scores of x on y, whatever the variables are. Okay. You can also say the true value of beta 1. Don't put hand because you're referring to population. True value of beta 1. When you say true value, you're referring to the population value because we are dealing with sample, so you can infer about the population. Right? You use x bar to estimate mu. You use beta hat to estimate the betas. Okay. Right? Yeah. Good. Any questions? Want me to repeat anything? Feel free to ask. I can do that. Okay. All right, so that's part A. Okay, let's take a short break and I'll go around and check your work. Okay? Right. Who wants to go first? Or this one? Okay. So it's 99%. So alpha is 1%. So this is compared to the 2 right? 2 tiers, 1%. That's 10%. 10%, 5%, 1%. And the case of 3 tiers, 25. Yeah, so you have it here. So very last one will be this house. Which is going to get everything else. You have the file? You ready now? Right now. No. Well, in this case, talking the same as and you should. Yes. Yeah. Yeah. You have to put M minus 2 is of freedom. Alpha is 1. You have to put that. Put our 1. And we have to know the language. Do something. You can do sorry. Middle. There. Yes. Oh, this is not testing. This is oh, you can try this. There's no. They all receive, but they have three. You have the input value input, and the input. So they are all received, and they are all using this. You can do in one. Uh, Unless the then you will ask it to you want to test it for them. Then you have yeah, that's basically it. But you can yeah. Most people prefer the feedback. You just look at R. You have a yeah. Ah, easier. Ah, it's just right. You have this like this is off. But this is what it's for. Sure. You have to do the people. how to get it done. You know? Ah, here's the thing. Ah, ah, is it clear now? Oh, um, well, it well it is. So alpha 99%, right? So alpha is 1%. One minus alpha is 91. Well, alpha is 0.01. One is 100. Yes, 1%. One is 100%. Minus alpha is 1% to get 99. Yeah, the same, right? One is 100. 99 is 0.99. One is 0.01. Yeah, yeah. You saw one minus alpha is in one minus one is zero, right? Wait. Okay. I'm gonna start the next one, and the rest I'll see you in the next break. Um. Yes. Oh, yes. Later. Yeah, boleh. Yeah. Huh? Am I free now? Okay. Yeah. You have to draw it. Oh, no, no, no. It doesn't cost. Yeah. 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 We don't ask for drawings. If I said, I was trying to do something. Just a calculation. Yes. But yeah, that's correct. Yeah. That's why it's alpha over 2. Ah. So you have 100%. Alpha over 2, so you have like, so if it's 1%, so we have 5% represent 5 over here, and we have 5 over here. So in the middle, you have 5. Ah. Yeah. Yeah. Yeah, yeah. Say it's a week. Yeah. So, you know, oh, I'm not good. Oh, oh, no. It's this one. That's the intercept. Ah, definitely. It's in fact large. So 13.9. Is it large? Is it the context? No, in the sense that why is bigger? In the context of this question, is it the thinking smaller? Is much more smaller than so that's one way to put it in context. One fifth of the segregation. Or you can compare that value with the mean of test score. Is it significant? Mhm. So you want to know, is it worth having small classes? Is it worth it? Yeah, you do it. Just put in context. But you want to decide whether, because having small processes are expensive. You want to see it is worth it. This is for policy. Okay, I get the impression that some of you are not sure how to get the value for the T critical value. So to use this table. So just to clear things up, just in case. So you have this value here. Oh wait, not this one. This one. Okay, distribution. So you have one tail and two tails. So that's one-sided or two-sided, right? Depending on the hypothesis test. So if it's not equal to 0, then that's two-sided. If it's larger than 0 or less than, then that's one-sided, right? But for confidence interval, it's always two-sided. So you have the plus minus in the formula. It's always two-sided, okay? So it's always two-tailed. Two-tailed. Right. So here, the significance level, that's the alpha. And you don't write it in percentage, you write it in proportion, you call it, in probability. Right. So 5.05. 1. 0.1 there, that's 10%. Okay. These are the common ones. They won't ask you some weird numbers like 3.57 significance level. I'm not going to ask that. Most likely it's 5%. If they don't say what level, assume it's 5%. That's the most common. 5, 1, 10%. Right. And on the left, it has degrees of freedom. So the n minus that's n minus k minus 1. And for different tables, they have different values of the kind of that they choose to put here. So usually they have up to 30. From 1 to 30, we have a increment of 1. Because those are where the values kind of fluctuate quite a lot. Right? But beyond 30, it doesn't fluctuate much. It doesn't change much. Like from 1 to, you can see from 3 point something, from 1 to 2, we jump from 3 to 1. That's quite a big jump, right? And the rest is quite a significant jump. Beyond 30, it's not big much of a difference. It's just the second and third decimal points. Right? Absolutely. Which is also why, remember, in the first you see that you consider the sample size large if it's more than 30. That is what. That's the bare minimum method. Now in research, they have a higher benchmark, 50, 100. 50 is as a bare minimum. After that, 30 they jump to 40 and 60 and so on. So here they have a maximum 120. So in your case, you have 840 minus 2. So that's large enough to consider it like a approximately normal distribution. The value will be close to the normal distribution. So here, they either put infinity symbol here, meaning large, very, very large, or they put normal. Okay. So that's the value here. 0.96. These values are okay. So in your case, you have 8, 8, we put here, 2 till 1%, 2 till 1%, go all the way down to 2.576. That's how you get 2.5. Right? Okay. I hope that's clear. Because you're going to use a lot of this. Yes? Any questions? In the exam, you won't have Excel or easy, so you can't get the exact value. You have to use table. If you can't get the exact value, just get the closest one. You can like 41 or something. Piece of freedom, so just use 40. Get the closest one. All right. All right. Yes. I know. After this, because I have to start part B first, and then after that we do that. So okay. Yeah. All right. Okay. A sample of 25 employees was taken. So this is looking at employee satisfaction, job satisfaction, and absenteeism. So basically, how much you are happy with this unit and how much you skip class. Okay. All right. Okay. So here, the interesting thing is, you are not given the full regression result. You are given some values, and you have to figure out how to get certain things that you need for hypothesis test. So you are given y hat equals to 13.6 minus 1.2x. So 1.2 is beta 1 hat, 13.6 is beta not hat. Right? Okay, so you have those. And then you are given x bar, which is 6, and you're given the sum of squared deviation of x. So xi minus x bar squared and the total of it. Does that look familiar? That's the partly the variance of x, isn't it? Formula. So you take that value, you divide it by n, 1 over n, then you get the variance of x. Right? But it's not variance of x. This is that. The sum of squared deviation of x. Okay. So 120. SSR, sum square residual, 80.6. ESS or SSE is the explained sum of square. Okay, 186.9. Okay. You clear on that? Okay. So this is how they can test you. Instead of giving you the regression result, they give you this, and you have to know the formula to get what you need. For example, the first one, you have to test whether absenteeism has a significant effect on, if job satisfaction has a significant effect on absenteeism at 1% level. So we run a hypothesis test. So T statistics, or sometimes called T calculated, is calculated in that way. Beta 1 hat minus beta 1. This is the full formula. Before this, I've mentioned is beta 1 is the coefficient, beta 1 hat over standard error, right? That's because most of the time, the null hypothesis here is beta 1 equals to 0. So this is 0 anyway. Especially in e-views, we just assume that this is 0. They calculate the t-test for when beta 1 in the null hypothesis is equated to 0. Right? But that's not always the case, as we will see in the next question. So this can take some value. If you want to test, for example, is the effect equal to exactly 1? Is the effect equal to exactly 5? Maybe you have some idea, you want to know if it's exactly that particular value. So you have to change it. Okay. So in this case, it's still 0. So it's beta 1 hat minus 0 over an error. So you get that. Now the problem is we don't have the value of an error. Right? We are not given that value. We're not given the full regression result, and we're not given an error here. We have to calculate ourselves. So that's the problem. All right. So we have to know what is the formula for an error. An error is that formula. An error square, which means like variance, right? So the deviation square is variance, so the error square is like variance. And that's a deviation, basically the same idea. So square is sigma hat square over the sum of the square deviation of x. So that's the formula. So you have to know the formula to do this question. Right? So make sure you have the cheat sheet. Okay. And now, do we have this value? We are given 130. That's fine. All right, so we can put that in. But we don't have a sigma square hat. The sigma square hat is this formula here. So you have to know that too. So that is the standard error of the regression. This is the error of the regression, which is basically the standard error of or standard deviation error. You think of it as a standard deviation of the residual, which is right here, 1 yi minus yi hat. That's u, isn't it? Yeah, that's the residual, the error term, by definition, right? We have u squared here over m minus 2. That's the, and you get standard error. But this case is variance squared of the residual. And that thing here is the SSR, sum square of the residual. That's it. My I minus y I hat. That's zero. You follow? Okay. So the few thing you have to know here, you have to know the formula for an error, the formula for sigma square hat, and to realize that this is SSR because we are given SSR. So we can use the value here. Okay. Okay. All right. So n is 25, so minus 2, 23. So SSR is 18.6. We can put that, so 18.6 over 23, and put that value over here, divided by 130. Okay, so it looks like that. The standard error of beta square is that value there. So we want the standard error, not the square, so we just square root it. We get 0.164. So that's the standard error for beta 1 hat. There you go. All right. So in the regression, they give this to you right straight away. No, they don't. So you have to know what the formula is to calculate. So this is how they can test it. So this is one of the more difficult. Okay. Okay. So once we have that, we get the critical value from the table 2.81. So let's use the table. See if we get 2.81. So it's 1%. So 1% is here. Two tail, right? Two tail 1%. And degrees of freedom is 23. So 2.807. So that's 2.81. Okay. So that's how you got that critical value. Okay. Yeah. Anybody want me to repeat or anything else? All okay? All right. Okay, and the T stat is 7.3037, which is the result of 1.2 divided by there's an error that we calculated 0.1643 over here. Okay? So we get 7.3037. Okay. Beta 1 hat is 1.2 divided by an error of beta 1 hat. We get 7.2. 7.3 is clearly larger than 2.1. Therefore, we reject our hypothesis and conclude that there is a significant linear relationship between job satisfaction and absenteeism. All right. Okay. Question B is almost the same, but a bit simpler. So this is about R square. So we don't have R square, we have to calculate it. And we have to know that is the formula for R square. Is explain sum of square divided by total sum of square. So that is SSE and SST. Same. Right? Okay. Yes. Explain and total. We have the explain given, but we don't have the total. We know the total is the explain plus the residual. Right? We are given the residual. Right? So the P is the explain plus residual, we get the total, and R squared is the explain divided by the total. We get R square of 69.9. So it says compute and comment. So comment is just you interpret it. So that's we can conclude that 69.9% of the variability in absenteeism can be explained by the variability in job satisfaction. So that's just interpretation of R squared in words. Right? Okay. And in other words, the differences in the level of job satisfaction explain about 70% of the differences in absenteeism across jobs. You can comment a bit further actually. This is just interpretation, not really comment. Okay, comment says that 70 is it high or low? It's quite high, right? 70% is quite high. That's pretty good. So that's the comment. Okay, you can go even further. In assignment, for example, you can go even further, say that it just makes sense that it's high because people tend to skip their job if they're not happy with their job. Okay. That's a little bit further analysis of the comment on it. Okay, so you can do that. This answer here is just interpretation of answer. Comment you need to put a little bit of thought. Okay. All right. Okay, question 2. Suppose that y and x satisfy the classical linear model assumptions. A random sample of size n equals to 250 is drawn and yields this equation here. Beta naught is 5.4 and beta 1 is 3.2. R square is 0.26 and standard error of regression, CR, which is sigma square hat, is 6.2. Test that. Let's say beta 1 equals 0 versus H1 and beta 1 not equals 0 at 5% number. This is a repeat of what we just did. So we calculated this beta 1, 3.2, divided by standard error 1.5, equals to 2.13. And of 240 is 1.96. Again, the table maximum just now was 120. So anything more than 120, we just take the value at the bottom, right? 1.96 or 5%. And we conclude that since the t statistics is larger than the critical value, we conclude that the null hypothesis is rejected, and that x is a significant predictor for y at 5% level. So I want to emphasize on the mention of 5% levels here. That's important because we're testing at 5%, we reject at 5%. If we test at 1%, we may not reject it. Okay? So basically, if you reject at a higher standard, I mean lower alpha than 1%, that's a higher benchmark. It's more difficult to reject when you get that. If you reject at 1%, you will reject at 5, at 10, and so on. If you reject at 5, you will reject at 10, but not necessarily at 1. Okay. They have asked something like that. Basically, that's because if you want to see in terms of numbers, the lower, the smaller the alpha, the bigger the critical value. Right? The bigger the critical value, the more difficult it is for t stat to be higher than the critical value. Therefore, it's more difficult to reject. For example, 1.965% you reject. 2.13 is rather than that. If you test at 1%, 1% is what? What is the 1% critical value? We just saw it just now. But 2.576, right? 2.58. 2.58 compared to 2.13, you reject now? You reject or not? No, right? 2.13 is not larger than 2.58. Therefore, at 1%, you will not reject. There you go. Okay? It does make a difference. Okay. Any question? So this is an interval again. 95%. So beta 1 hat plus minus critical value times standard error. 3.2 plus minus 1.96. That's equal to 5% times 1.5. That's for you. So 0.26 and 6.14. All right. Let me ask something. How many approaches to hypothesis testing are you know? This is the critical value approach. That's because it's critical value. What's the other one? The p-value approach, right? What's another one? F? No. That's another test. So for T, you have 3 approaches. For F, you also have the 3 same approaches. You can use the F step for value, p-value for F step. What's the other one? The confidence interval approach. That's right. Just a bit less common. So here, you can use this for hypothesis testing. How? If p-value, if alpha, if the p-value is less than alpha, you reject. Right? That's the rejection rule. For critical value, if the t stat is larger than the critical value, you reject the hypothesis. How about this? Yes, that's right. If 0 is not within the range of the interval, then you reject the hypothesis. Meaning, this is 95% confidence interval, right? So there's a 95% chance that 0 is not in there. 95 basically we're saying that there's no chance that 0 will be in there. So it's significantly different from 0. You get the logic? Right? If you have 0 in there, meaning you have -5 and +5, for example, so 0 is in between. So there is a chance that 0 will be the value of beta 1. So it is not significantly different from 0. So, you do not reject my hypothesis. Okay, there's the 3 approaches. And all these 3 approaches must be consistent. If you reject one, you must reject with the others. So there are 3 sides of the same coin. Which one can you use? Anyone. It does not matter. Depends on what you prefer. Depends on your purpose. Most of the time, people prefer to use p-value because it's easy, right? Just compare to alpha, you can see the p-value straight away. You have to calculate. You have to look at the table and all the crap. But so it's the simplest one. More convenient. All right. If you find one is not consistent, something is wrong somewhere. So it's good if you want to make sure you use more than one approach and see if you get the same result. You know, for example, because you have no time, right? For assignment, maybe you can, right? Just make sure that you understand and make sure that you don't make any mistakes. Yeah. Right? Oh, and see, suppose you learn that y and x are independent. Would you be surprised? After doing all the tests, would you be surprised that it's independent? Then there's no relationship between them. You would, right? Because we have done the hypothesis test, and they are significantly related. There's a significant effect of y on x. So you would be surprised. Right? So you should not be dependent. Already proved that they're not. Okay, this question P is a little bit tricky. It's not very important conceptually. It's hypothetical. But I'll try to explain in a non-confusing way. So now, suppose that y and x are independent, hypothetically, and many sample of sizes n equals to 50 are drawn. Meaning instead of just one sample, you get like 1,000 samples, each with size 250. Right? Regressions estimated, so you estimate 1,000 regressions, and A and B are answered. In what fraction of samples, in what fraction of the regressions, how many of those regressions out of 1,000 would H not be rejected? And what fraction would beta 1 equals to 0 be included in the interval? Okay. So basically it's asking, if you have 1,000 regressions, now let's look in the context of this first. So if you have 1,000 regression and you run this test 1,000 times, how many percent of those 1,000 regressions would you expect to have a significant result? If you test them at 5% of it. How many? Out of 1,000, how many regression, when you test it, you expect to get a significant result like this? And the other 5% is not significant. Ah, shoot, I just gave you the answer. Okay. How many percent? 95%. You get the idea? So that's another way to see it. You test this, right? If you only run one regression, but the power of regression and this all this formula version, you can infer as if you ran 1,000 regressions and you found that 950 of them have a significant result. If you do that in real life, wouldn't you be convinced that, oh yeah, there is a real relationship here? Would you? If you're not, then you put a higher benchmark. Instead of 5%, that's at 1%. Right? So you need 990 out of 1,000 result to be significant. Not convinced. Do alpha 0.5%, 0.1%, which people actually do, depending on how rigorous your field is. For social science, they can use 5 or even 10%. For things like medicine, margin of error is much smaller, right? So aeroplane, rocket science, and stuff like that. So they need a very small alpha. So they use 1%, 0.1%. They actually use this kind of number. You want to make very, very, very sure. You get the idea? Yeah. So that's what this is trying to explain. So if you hypothetically, the question just now is that if it's the other way around, if they're actually not significant relationship, they're actually independent, so how many percent you would expect for it to be not significant? 95%, right? You will find 95% of the time, 950 out of 1,000, that the result is not significant. 5% will be significant. So the 5% is like some special cases. Look at that money. You can't get 100%. How can you get 100%? The whole population. That's the only way you get 100% confidence. That's every single one, right? Which is difficult, expensive, time consuming. Well, we do scientific instead. Right. So that's basically question. Okay, question 3. Can keep going? You guys okay? All right. Okay, so file 401k subs. So this is like our EPF and tax return. So you know what tax return is? So you have to tell the government if you have extra income besides your stable income. So you guys are not earning yet, right? You don't have a stable income. So this is the month, the deadline. So if you are below a certain threshold, you get your money back because the government take your money first. If you earn 5,000, for example, if the tax is like 5%, so they will take 5% first. You don't see the 5%. And then if you have you spend on some tax exemptable items like medical costs, education fees, like your fees, which is why your parents always ask for your receipts, so you can claim the tax. Books, they have some limits. Buy laptop, so you can say I spend this money on these things, a charity on these things. Then these things are not taxable, it's tax deductible, so give me back 5% of these expenses. So they give you back. But if you have other income like shares, or you sell a house, or you do other business which is not paycheck by paycheck, you have to tell the government, this is what I have, so I owe the government tax. So they will ask for your money. If you don't do that, transparently, they come and audit you, and they can fine you, or you can go to jail. So it's serious stuff. Okay, so anyway, so this is what they have in America. They call it 401k. Be like EPF and tax as well. How many single person household are in the data set? Okay, so we have family size there. So for single people, what is the family size? 1, right? Yes? Makes sense? Family size of single people is just 1. They're living alone, right? So for the data set, we change the sample to only include single person households. Okay. If I have a file here. We have about 9,000 plus families in this data set. Okay, 9,200 plus. So we want to restrict to only analyze single people in our sample. So you double click sample here. Okay, see that? There's a word sample. It doesn't look like a button, but you can double click it and you'll see that. Okay, so in the if condition at the bottom, put f size, family size equals to 1. So we only include in the sample family size is equal to 1. So when you run regressions, histogram, or whatever it is, only includes those people, that portion of the sample. But you're not deleting anyone. Okay? So if you do that, for example, uh, so you still have data on all the other families, but your sample is only single single people sample. If you need to do analysis for the rest, you can just delete that if condition and you can run it again. That's convenient, right? Otherwise, you have to separate it and delete and so on. So that's very tedious. So this is easy. This one function is interesting. So now you have, instead of 900 plus, you have 217 people in your sample. All right. Okay. Okay. So estimate this regression, net financial wealth on income and on age for 217 people. What's the difference between net financial wealth and income? What's the difference? Isn't that pretty much the same? After deduction of tax, actually income is usually net income in the sense that they deduct the tax first. What you get is the disposable income. Sorry? Includes other assets like what? Property, house, stocks, things like that. That's right. Also includes your liabilities. If you have house loans, you have debt, education debt, whatever it is, right? So that includes as well. So it is possible to you for you to have negative financial wealth versus net, right? So you have more liability than asset, then you have negative. Possible. But income, you can't get negative. It's paycheck to paycheck. So you always be positive. That makes sense? Okay. I don't think that's negative in this case though, but it is possible by definition for financial wealth. So we have that thing over there. Regression. Um, let's interpret the slope. So we have coefficient on income 0.8 indicates that for one extra dollar in income, you would predict the net financial wealth to increase by $0.8. That's 80 cents. Holding each constant. So that's 5%. That makes sense, right? Because income will be a large part of most people's wealth. So for every $1 increase, 80% increase. So there are some other factors there, the 20 cents that contributes to wealth, such as income. That makes sense? All right. On age indicates that holding income constant, if a person gets older by 1 year, the net financial wealth increases by $843. Okay. Makes sense. Right. The intercept is more interesting. So intercept is negative 43. Okay. Is it meaningful? So if someone has income of 0 and age of 0, income 0 is possible. That's possible. But age 0 is a newborn baby. So so it's not likely for that person to have any meaningful wealth. So in this case, if you're a newborn baby, you have negative 43 already. Well, that's sad. You already have some debt, which is not actually that far fetched because if your country has a lot of debt, then actually you as a future generation have to bear it in the future. So you do actually have liability already the day you were born. So right, parents have debt, so when your parents pass away, you have to carry that debt. So, oh man. But we're not analyzing to that level. This case, -403 is not very meaningful. Okay. All right. Because especially in our sample, we don't have people with zero income and zero age. That's in terms of data, that's what you would answer in this. Okay. All right. Okay. So this is interesting. Now beta 2 is not equal to 0 anymore. It's equal to 1. So that's then the effect of h on net financial wealth exactly equal to 1, or is it less than 1? This kind of question, this is straight away. They just give you the null hypothesis and the alternate hypothesis. But usually they don't give you this. You have to figure out what the hypotheses are. For example, they can answer that test whether the effect of h on net financial wealth is less than 1. For example, to ask you that. So if it's less than 1, the less than 1 part will be the alternative hypothesis. That should be H1. Should be the alternative hypothesis, and therefore what will be the null? Is it equal to 0? No. It should be equal to 1. You get the see a difference there? You get the idea? Right? So they might ask you, test if the effect of H on net financial wealth is exactly 1. Then exactly 1 would be the null hypothesis. This will be not equals to 1. Okay? So the null hypothesis has always have to be equal to something. 0 equals to 1. And this one has to be less than, more than, or equal to. So that's equal. Okay, so in this case, we have to calculate ourselves the P statistic 0.843. That's beta 2 hat minus 1, which is the value of beta 2 from the null hypothesis, divided by the standard error given there, we get approximately -1.71. Okay. And then degrees of freedom is n minus k minus 1, 2017 minus 2 minus 1, 2014. 2040 degrees of freedom. And that is 1.282. Okay. Is there anything missing here? Do you see anything wrong? Anything that's incomplete? This side is okay. The piece of freedom is okay. How about the critical value? It should be negative, right? Why should it be negative? Because it's less than. Because the H1 is less than. Okay. All right. It should be negative. It should be negative. So and then, so therefore, this statistics is less than this. Negative 1.71 is less than negative 1.2. Therefore, we reject our policies at 1%. Okay. At 1% significance level. So be careful. All right. Has anyone used like a blanket rule where you think the absolute value of t-stat and the absolute value of equal value, and if the t-stat is larger, if the absolute value of t-stat is larger than the absolute value of equal value, we reject our hypothesis. You do that? You do that, right? That's simple, not much to remember. But here you have to remember if it's negative, you have to be less than, positive, to be more than, so on. That's okay. You have a question? Is it? Let's see.
1.282 is what, 10%?
10%? It's a mistake there. Awesome. You're right. 1%. It should be 2.326. I didn't check this. Yeah, that's quite clearly wrong. Okay. Ah, see, two classes didn't notice. I didn't check. I just take it from the C. I'm sorry about that. Okay, you're right. So one tail, 1%, 0.01 is 2.326. Exactly. So this whole thing is wrong. Very good. I like this. Okay. I like it. You find mistakes. So it means you're paying attention. Okay. Very good. Okay. So now the whole thing is wrong. So that should be negative 2.3 something, right? 326. 326. So do we reject it? No, right? So it's not significant. Right? So it's not significantly different from 1. There you go. Okay. I have to correct this later and show the minutes. Okay. So here should be 2.326 negative, and clearly that is not less than that value. We do not rely on this. Thank you. Yeah, I think that's correct. Okay. Everyone okay with that? Yeah? Okay. Thank you very much. All right. Okay. Okay, now question E. If you omit H from the first model, take it out and estimate the coefficient, would the coefficient on income be much of a difference? Well, from 0.799, it has changed to 0.82, which is not a very big difference, right? Roughly speaking. It's not a significant change, it's not a change in sign. Last time, remember when we have the abdominal circumference and body weight and body fat? When you add another one, the sign change. Body weight, right? So that's significant. So this is not really significant. So the idea is that why is this? That's because the correlation between income and age is low, 0.039. So there is an omitted variable bias here because age is significant, which should be included. This model is better than that. R square is 11, 12 there, here's R square is 8. So this is a better model. But if we do exclude that, does it make a big impact? Not so much, because the correlation between these two is low, and therefore the omitted variable bias, the bias in this is a good one. Human bias, this is a little bit bias, but the bias is small. Not very significant. So that's the point. But still, this is preferable. Okay. All right. Okay, the last question. Growth and education. GDP per capita and average years spent in education in the 2005. So from an economic point of view, what direction would you expect? Relationship between education and economic growth? Negative or positive? Positive, right? Obviously. Better education, better workers, higher productivity, more innovation, better GDP per capita, higher economic growth, more development, right? Makes sense. All right. So we expect a positive slope here. So we run the regression, GDP on education. Okay, it's positive and equal to 2734.2. If plus a 1 additional year of education is associated with an increase in GDP per capita of $2,734. Okay, makes sense? Now, that's not very interesting. The intercept, negative 9,000 plus, does not make sense, right? But this might result in the regression not being well defined in the sense that maybe there are other factors. Maybe the measurement is not accurate. Okay, so we want to try to make this meaningful, the intercept value, the negative 9,000. But the model itself is pretty good. Education is significant, and R squared is almost 70%. It's quite, for a one variable model, it's pretty good. Okay, but let's see how we can make the intercept more meaningful. Okay, so this is interesting. I think this is the most interesting part of the tutorial. How can we address this now? Let's try creating a new variable. Instead of education, we call it education new and calculate it as the difference between a country's level of education and the global average of education. Okay, great idea. So for every country's average education level minus the global average education level. So what do you see here? You will see the difference, the gap between a country's education level and the global level, right? What's the benefit of this? Just based on that calculation. What's the benefit? What's the difference between this one and just looking at the education level of each country by itself? What can you tell from this? Will you have negative and positive values for this new variable? You would, right? So meaning, if you're a positive value, meaning you have an above average level of education for the country compared to the global average. If you have negative value, meaning you're lower than global average country. Right. So since there's a strong relationship between education and GDP, so if you have above average education, you should have above average GDP as well, and vice versa. Right. So that's one insight is interesting from this way of measuring education. Okay, now, so we drop the old education variable, we use the new one, and we run regression again. Okay, so like that. Interestingly, the slope parameter 2734 has not changed. It's the same. Using this new variable, even though the values are all different, right? Because you just calculated it. But you can still look at the effect of education on GDP. You can still interpret that variable as for every 1 year increase in education, GDP per capita increases by that much. It's still the same. Why is that? Even though you have changed the variable.
It's still calculating based on your.
Okay, that's true.
So before that is like you for the new regression you just include the average of the world into the constant. So the change doesn't change.
The global average is a constant. Understand? Right? Yeah. So because, for example, because you're deducting the exact same value, global average is one constant, which from every single value. So the shape of the distribution of education doesn't change still by the value of the global average, right? It's shifted, but the value itself actually doesn't change. Right? This is why you can still calculate the effect. It will be exactly the same. Which is also there's one technique. If you want to use log models, you can't log negative values. Right? It's undefined. So what do? If you have negative values in your variable, but you want to log the value. If you have -5, for example, as the minimum, you just plus 10, for example. You plus 10 for every single observation for that variable. So then the minimum value will be 5. So -5. Yes? So everything will be positive, then you can log them. But the effect will be the same. Even though the values are different, but the slope will be the same. You're interested in the slope anyway, right? That's what you want, the effect. You can still do that. So that's one technique for log models. Sometimes you can't help having negative values, you still have to log them. You can't log negative values. All right, there you go. So that's why, that's right. Why is The value of the parameter has not changed. Now, let's look at the intercept. That's more interesting. So now it's 10,976 instead of negative 9,000. Okay. The interpretation is still the same. So 10,976 is the value of GDP per capita when education new is zero. But now the meaning of education new is zero is different. What does it mean now? Does it mean you have zero education? The country, nobody goes to school. Does it mean that anymore? Previously it means that, right? But now what does it mean? It means what? It's the global average. If your value for that variable is zero, means your country has the exact same level of education as the global average. Right? So now you interpret that if your country has a global average education, your GDP per capita will be 10,000. There you go. So if you have higher than average education, your GDP per capita should be expected to be more than 10,009. Lower, lower than 10. So that's like the benchmark. Just in red. You change the way you measure something, the way you calculate the variable, you can interpret it differently in a more meaningful way. Okay. That's how you be a bit creative with the regression. Okay. Is that it? Okay. This is not very interesting. This is just R squared. So this is R squared 69.3. So 70% is explained by education, which is quite high. Is it significant? Yes, significant. T star is 13.26. Or you can just look at the p-value. P-value is 0, so it is significant. Okay, nothing very special there. Okay. This one also is just the confidence interval, but I want to show you something that can use EFUs to calculate this interval for you. So you don't have to look up the table for the critical value and all that. You can get the exact critical value. So if you want to try, okay, since I have it here, what? Okay. Okay, so okay, in your regression output, click view, coefficient diagnostics, and look for confidence interval. So you can use it for your assignment. But you have to state the formula. You have to state that you know what the beta hat is, what the degrees of freedom is, what the the alpha is. Okay? Critical value, you need to show all that. Okay, so now EVS is offering 3 different levels: 90%, 95%, 99%. You just click that. So we have that, and you choose whichever one that you want to use. Okay. You can't get this value to the table because the table doesn't have exact degrees of freedom value. You have to use Excel. Okay. Use Excel function. Function to get this exact critical value. Here, you use the point using the exact. Okay. 90%, 45, 95, and 99. Okay. Yeah. Okay. So take note of that. Okay, let me to repeat. View, coefficient diagnostics, and confidence interval. All right. All right. Okay, that's it for today. Thank you very much. I'll see you next week. You have extra class today, right? Lecture? So make sure you don't miss that. And for the rest, which I have not checked your homework, okay, I'm gonna go do that now.